mass term for Dirac fermion is this. You also know that this can be written as is that clear to everybody? Okay, this is the mass term. Kinetic term is this plus gauge interactions, whatever it is, right? Or maybe a covariant derivative with their gauge interactions. And this can be written as you know that? Is that clear? If I change my definitions, what happens? Kinetic energy is unchanged, mass term changes sign. Either this way or equivalently the other way around also. Either redefinition will change my sign. Huh? It's just change a variable. In this form, I think pi by 2 or pi, is this, does this change the sign of left and right? Or pi? No. By chiral, this is a chiral transformation, right? That yeah, I mean in this way I think it's more transparent. So by redefinition of your variables you can change the sign of your mass term. So what is mass of the Dirac field is mod of the parameter m that appears there. So that was one technical point that it struck me that it would be there. And did any one of you answer what about the real parts of eta 1 and eta 2? First thing is you didn't get the imaginary, you didn't get the mass of the scalar, right? Complex scalar.
But eta 3 is massless.
That is straightforward. No, I think that is algebra error. If you did you get the mass of the complex scalar right? And that was the combination that it came in, imaginary eta 1 plus imaginary eta 2. Huh? Did you also get that right? So which means you have not done your algebra carefully. If you do algebra carefully, you will get it. You've done it, not done it carefully. If you, which means error in algebra. Real parts will cancel.
Real parts won't cancel unless we're in a certain gauge. That's the last question.
This guy understands it well. No, okay. No, from the mass term they will disappear. Right? From the kinetic energy term they will not. And derivative terms they will not. Right? Did you get that or not? Tell me. If you have not gotten it, we'll understand it, how it happens. So answer, don't feel shy if you have not gotten it. Doing an error or not understanding is not a crime, but not making an attempt to understand is a crime.
So is it like real part of eta 1, eta 2 have no mass terms, so we make them 0 and the imaginary part prevails, something like that. I mean, they will not cancel exactly algebra.
When you do the algebra, the real eta 1 and real eta 2 don't appear in the mass terms. There are no square terms of those kind. But they are there in the kinetic energy pieces, derivative pieces. Right? Did you get them or not?
For this thing, we are expanding the 5-4 term part.
For mass, that is what it is. So from mass, from the potential part, when you expand the potential around the vacuum, and then you will not get any term which is square of real part of eta 1 square, eta 1, or square of eta real part of eta 2.
That must come, but we are not exactly.
Yes, no, that's algebraic errors. You do it once again, or maybe sit with one of these guys and who has done it. That's an algebraic.
I think I know where that error could come in. It's a mod of phi b star phi c, right? Whole squared. So that's actually phi b star phi c, phi d star phi e, and there's an epsilon which is signs. So if you don't put the conjugation properly, then
What we did was we put
You want me to do it on the blackboard now? It's an elementary exercise. Let me see if I can remember how to do it. This is what it was. Let's write it in longhand. Is that right? Star shifted to the first one because of conjugation. And then you know how to contract these two? These two objects are delta B, D, delta C, E, minus delta B with E, delta C with D. So delta B with D. Delta C with delta E. This term is delta B with E. Delta C with D. B, B, and this is B, B. Yes, C is D. Right? And now you put phi B is A times eta 1, eta 2, eta 3, this is what. So phi B is eta 1 square plus eta 2 square plus eta 3 plus A square. That is eta 1 square plus eta 2 square plus eta 3 square plus 2A eta 3 plus A square. and phi b star is eta 1 times eta 1 star, eta 2 times eta 2 star, plus eta 3 plus a, eta 3 plus a star. That is eta 1 star plus eta 2 star plus eta 3 star plus a times eta 3 plus eta 3 star plus a square. Now what is this object? Is phi b star square. So let's do the square of this object. That is eta 1, and let's keep only quadratic terms because mass is only quadratic terms. So let me not keep all the terms, only quadratic terms. Quadratic terms are a square times eta 1 square plus eta 2 square plus eta 3 square, this times this twice. Then there is another quadratic term which will come from square of this. Did we get it right? Well, let me put 3 down. I think we got it right. And then that was the first term. The second term is this mod square of this object. And keep the quadratic terms. Now here, quadratic terms are a square, eta 1 square, eta 2 square, eta 3 square, eta 1 star square, eta 2 star square, eta 3 star square, right? This times this and this times this. But then there is also this term. And subtract them. Subtract them. So V is now e square by 2 quadratic terms. Now if I subtract this from this, this is what all goes away. That's 4 this times this. Now, does the eta 3 square yes, there is an eta 3 square here, star, this goes with this. This goes with this. Now there is 2 eta 33 star here and 2 eta 33 star here. So this and this cancels this. So done. And now collect the rest of it. Is twice n1 n1 star twice n2 n2 star minus n1 square minus n2 square minus n1 star square minus n2 star square. Is that clear? And that is minus e square by 2 eta 1 minus eta 1 star, no, something, yes, square plus eta 2 minus eta 2 star square. This object is twice the imaginary part times I square. Twice the imaginary part times I, square of that is, so that is 4. So twice is, so 2 square is 4. So you have 2 e square and the sign changes because of I square. Imaginary eta 1 imaginary eta 2 square. A square I missed everywhere, right? And that is 2a square e square imaginary eta 1 plus I imaginary eta 2 mod square. Was this an error? Some calculation error somewhere you must have done.
Last year,
Somewhere.
replacing from class.
And it gives you the right sign also. So this object you interpret as m square of this field. And now there was also an issue of now real R1 and real eta 1 and eta 2. They are not anywhere here, right? Also, did you get what was the mass term for the gauge boson? Massive gauge boson? Did you get that right? Did you get that right? Because if you do the expansion, you would have gotten mass term without an E.
Would that again come?
Huh?
In kinetic energy term, there is one.
There's an extra E. So you notice that, and that is what you rescale in order to interpret it mass, because kinetic energy normalization should be half in order to interpret it per mass. So that E square goes away, goes into the mass term. So that's one little point. What was there any other point? Yes, now that leaves imaginary eta, real eta 1 and real eta 2. They are not in the potential. There are no quadratic pieces for them from the potential, but they are in the kinetic energy. So what happens to them? Where are they? I did not list them as physical fields. He knows the answer. Does anybody else know the answer?
It is not appearing in the expense in that case.
the W plus and W minus that you constructed and got the mass for it is a massive vector gauge boson. But W plus and W minuses are constructed from A's. But this is a gauge theory and A's have only transverse components. So you're writing a mass vector mass field which has to have both transverse and longitudinal components. But where are the longitudinal components? R1, the imaginary eta 1 and imaginary eta 2 are those longitudinal modes, which means you should be able to absorb them redefining W. Sorry, real eta 1 and eta 2. You should be able to absorb them in redefining W, which is a massive gauge field, W1 or W2 or W plus and W minus, which are massive gauge fields. Therefore, they need longitudinal degrees of freedom also. In some gauge, that's what he thinks, that I can make longitudinal degrees of freedom 0. That's what he said. But in some gauge, gauges that eta 1 and eta 2 don't have any real parts. Right? Now, what does that mean? Eta 1 and eta 2 don't have any parts. What we had is phi b was eta 1, eta 2, eta 3 plus A. This theory is gauge invariant. So I can do a gauge transformation on this phi. My gauge transformation has 3 parameters because it's an SU2 gauge transformation. But I want to leave one gauge transformation, gauge invariance as unbroken, the U1. So I could play around with 2 parameters. So I can make transformations of this object in such a way. Now this was real eta 1 plus I imaginary eta 1, real eta 2 plus I imaginary eta 2, real eta 3 plus I imaginary eta 3 plus A. I can make it a gauge transformation subdue, new object. I can just rotate away 2 of them because I have freedom to do gauge transformations orthogonal to the U1 part, which is described by 2 parameters.
The eta 3 remains the same.
Well,
Eta 3 remains the same.
yes, all right. I do rotations only. So I can always do this. So that's one way of understanding it, why the eta 1, real eta 1 and eta 2 have gone. That's his way of understanding it. This is what you meant? Well, you said it in words, perhaps you didn't mean it. Huh? The other way is that you leave it, I mean, but what you have is you have W1 square in the fields W1 and W2 or A1 and A2, or maybe A, right? We call it A. And then W was constructed by. This is what you found after putting in the vacuum expectation value of the scalar field. And in addition to that, you also have d mu of real eta 1 square plus d mu of real eta 2 square plus the imaginary parts. You also have this. Now this combination is part of what gauge invariant combination. It has all the other pieces also, because it's an f square piece, right? That's gauge invariant. But this object that you have gotten is not gauge invariant. So if I make a gauge transformation on this now, changing a mu 1 to a mu 1 prime, which is old a mu, plus a derivative of eta 1, maybe some constant that you would need here. I can always make that. Maybe 1 by m or something here. Just check what exactly is. And similarly a2 to a2 prime Solely real, yes, you're right. Something of this kind, and maybe other pieces, right? Because it has to be, gauge transformation is covariant derivative of the parameter. This is one piece and then there are other pieces. But derivative is only here. Now if I put this into this, I'll have the square of this object. That's going to give you a d mu eta, real eta square. That's exactly the same structure here. And if you look at the signs properly, I think the signs here are relatively opposite, right? So by an appropriate gauge transformation of this kind, from this term, I'll generate terms which will cancel precisely this. This is doing gauge transformation after having arrived at the end answer. The earlier argument was do gauge transformation in the beginning and then get to the answers. Is that clear? So now new fields are these prime fields. But this is a gauge invariant piece, so this doesn't change. I write it in terms of primes. The mass term is written in terms of primes now, but this term is absorbed.
So if we work with these prime fields now, our massive gauge bosons will already include the real part of it.
That's right. Now it's that's what we have done. See, the point is that this was supposed to be only having transverse degrees of freedom. By adding this to it, we have added a longitudinal degree of freedom to it. Is that clear? So you can do either his way or you can do it this way. His way is a particular gauge in which real eta 1 is 0 and real eta 2 is 0. This is saying that real eta 1 is not 0, real eta 2 is not 0, but by a gauge transformation I can absorb real eta 1 and eta 2 as the longitudinal components of the massive vector field W1 and A1 prime and A2 prime. So that was this subtlety. And this exercise was again because what the question you asked, you wanted to understand spontaneous symmetry breaking better. Now, in this context, no. Now if you understand it here, you understand the standard model also, right? Okay, done. There's, okay, from last lectures, is there anything, did you understand the Witten effect? We did last time Witten effect. How does a pure magnetic monopole acquire a charge which depends on the theta term? Because of adding a particular structured total derivative to the Lagrangian density. Adding the instanton density to the Lagrangian density that changes the electric charge of a pure, otherwise pure magnetic monopole. Was that argument clear? Because if you have any questions that I will take now, otherwise I will just move on now to some further discussion. Or you didn't get time to look at it because you were preparing for the rest of the exam. You ignored that part. It could have been in the exam, right? Did you get that? The Noether construction that I did, is that clear? Huh? That's the only technical point in that argument. You have to do that Noether construction. Okay, then I think we'll move ahead now. So what we did was, let me put one line summary of what we did last time. Jarjoy-Glashow model. In Jarjoy-Glashow model, the charges lie on a lattice. That's what we argued. And the lattice was given electric charge plus I, magnetic charge, is given by E times n plus m tau, where tau was theta by 2 pi plus 4 pi I E square. And m and n are integers. We did it for some values of m and m. We found n and m are 0 or plus minus 1 values. Let me take theta to be 0 and list what we had obtained for theta equal to 0. Theta equal to 0, the spectrum we had obtained, particle which we called Higgs. This is in BPS limit, right? BPS limit. And BPS limit was when the potential is made through the lambda coupling going to 0. And what was the mass of the Higgs field? Was 0 in this limit. Otherwise it was lambda times square root lambda times some vacuum expectation value. And if I list electric and magnetic charge assignments, it had an electric charge assignment 0, magnetic charge assignment 0. And spin 0. This was one particle in the perturbative sector of the theory, the Higgs particle. Then we also had a photon, what we called a photon, a massless gauge field, and we called it a photon. Mass 0, electric charge 0, and magnetic charge 0 and spin 1. Then we had the massive gauge fields, which we call W plus and W minus, with the mass given by vacuum expectational times E. And the electric charge for these objects was plus minus E. And magnetic charge 0. And these are spin 1 massive gauge fields. Then we had monopole. Magnetic monopole. And magnetic monopole, the charge mass was A times G, but G is the magnetic charge. And this assignment is 0 and G. We also had an anti-monopole with the same masses, except that the charge was minus G, and mass is here mod. And the spin 0. Then we had dions. D with mass A mod of Q plus I G. This is what the mass for a dion turned out to be. And electric and magnetic charges were 1 unit of E, Q was E. Remember, G for this theory was 4 pi by E. Notice for the whole spectrum, for all these particles or states, mass is always given by A Q plus I G mod, or that is A Q square plus G square square root. That's trivially true for this, trivially true for this. That's true for W plus and W minus also. That's true for pure monopole also, and that's true for the dions also. So for in the BPS limit, these are BPS states, mass is always given by this formula, which is the saturation limit for the mass formula. If I did not have the BPS limit, which means if I did not have V phi equal to 0, then the mass would have been different from this, but this would be the saturation limit of that mass. Mass would have been greater than this. But in the limit of BPS limit, the mass is given exactly by this formula. All right. And also, and electric charge is given by N times E, and magnetic charge is given by 4 pi m divided by E with n equal to 0 plus minus 1 and m equal to 0 plus minus 1. Those are the solutions we explicitly saw in the theory. This mass spectrum has a duality, and the duality is E going to G, where G is 4 pi. These are dual. E goes to G, mass is this. Maybe I should have put mod here also, right? This mass is mod, E plus and E minus, right? Or if you take E to be positive, then I think that's fine. We take the E to be the smallest positive value, then that formula, that's all right. So they go into each other. Electric charge goes into magnetic charge. And masses. So there is a certain kind of a duality property here. And for dyons that's true also by construction. Now looking at this, there's a gentleman called Montaigne and another guy called Olive. They made a conjecture. Duality should be a property of George I. Glashow Higgs model, this model that we have, in BPS limit See, we saw this property at the classical values of the masses. What these guys conjectured that this should be true quantum mechanically. Right? Can that be true? Can this conjecture be true? No. Generically, no. Why? Reasons. Number one, for this duality to be true, an important ingredient is BPS limit. That is lambda going to 0 limit. Can I maintain lambda to be 0 even quantum mechanically? The answer is no. Generically, no. Very special circumstances, maybe yes. That this limit or B phi 0 cannot be maintained generically under quantum perturbation. Is this statement clear? Can anybody give me a qualitative structure of the argument why that is so? At the tree level, if I start as lambda equal to 0, which means V phi is 0, that means I have no phi square term, I have no phi 4 term. But I have a vertex like that in my theory, right? I also have a vertex of this kind in my theory, gauge fields and scalar fields. When I do one loop perturbation theory, I will generate effective vertices of the kind strength of this coupling is given by gauge theory, because it's a coupling from the d mu phi square term. Strength is E here, strength is E square here. So this diagram would be order E square, this diagram will be order E square, this diagram will be order E4. So even if I did not have classically these kinds of theory, but at one loop I would have generated phi 4 term, phi square term. There is no reason to expect that these are 0. So at one loop level I would have a potential which is non-zero, and potential being non-zero means phi 4 being non-zero is the lambda would have become E4. Lambda classically was 0, but lambda one loop is order E4, because this is phi 4 term. Is that clear? So generically under quantum perturbation I cannot maintain that potential is 0. So I cannot maintain BPS limit. If I cannot maintain BPS limit, there is no reason to expect for me to have this duality. Okay? Except in special circumstances where for some reason all these terms are 0. Means that I have this term and then I also fermion terms, right? I mean, I didn't write the I could have Yukawa couplings. I could have fermions coupled to my theory. That was one of the exercises, and exercises you did it, right? In fact, one exercise you did it earlier was when you found beta function to be 0. Then one exercise was in this exam when you found beta function to be non-zero. But you have fermions there, you have scalars there. So in addition to this, you also have couplings of fermions. Which will also give diagrams of this kind. Say for example, you would get fermion diagram, or you would get so, but in some special circumstances, it's possible to imagine that fermion loops, you remember, have a negative sign as compared to boson loops. So these contributions will come with opposite signs. I may be able to cancel them. In order to cancel them, what do I want? I want their numerical answers to be exactly same. But before I do the numerical answers, I also want their dependence on the coupling constant to be same. So at least one thing I discovered already here, that the strength of this coupling also has to be order E, so that this is E square to cancel this. And this would be E4, right? E. So what it tells me is that in order to arrange, if at all I arrange this cancellation, the couplings of the fermions to the scalar field and coupling of gauge bosons. Coupling of gauge bosons is E, that's all right, but it also depends upon what representation the scalar field is in, right? The scalar field, whether it is in triplet or doublet or for SU2 theory, let's say, it could be a doublet, it could be a triplet, or it could be a high dimensional representation. So it would be E times the corresponding FAB symbol, corresponding corresponding the matrix, corresponding matrix, not FAB, corresponding matrix. FAB symbol is in triplet represent. All of them are in triplet. So this also tells me is that not only these E's have to be matched, but those representations have to be such that this happens. So in order to have BPS property, we have realized that generically it's not true, but in very special circumstances we may be able to arrange that it is true. One is that the strength of the coupling of this and these fermions, and they have to be same. These objects have to all lie, for example, can lie in the same representation, so that in this we have the same C in the group theory contributions. So the two exercises that you have done had that property. All fields were in their joint representation. And the second exercise, if you remember now, the exam exercise, the couplings were all E's. Yukawa coupling was only E. Here, from the exercise, right? So we had, in some sense, those models tuned the couplings and representations. But that still is not good enough to say that this can cancel. But now the other numerical factors, have to work out.
The first diagram will be perhaps two gauge bosons going to a scalar.
Two gauge boson. Here. Oh no, sorry. I see. There is this vertex, and there is this vertex is also there, right? There is also this vertex, right? Or maybe this is not there. This is what I should have written, right? No, sorry. This vertex. Maybe I should have written this vertex. That's what is here. You're right. So something of this. That's the counterpart of this, right? This is additional. So some qualitative picture is emerging. First is that the couplings have to be same. Now the group theory, not only gauge couplings have to be same, the group theoric structure has to be same. And then there is a possibility that I may be able to cancel it. And in the two exercises that we have done, that exactly is the property. But what does that mean? It means is that fermions and bosons, their couplings and their masses also, because when I do in the loop calculation, the masses come in, right? In the propagators, have to be completely related. in order to this cancellation. So which means properties of the bosons and properties of fermions have to be completely related if this has to happen. And that's what supersymmetry is. So in supersymmetric theories, if you have at the tree level BPS limit, even at one loop level, you can maintain it. So what this tells me is that this cannot be generally true, but can be true in supersymmetric theories. I don't know if you have already realized it. The exam calculation that you did was you did a beta function calculation for n equal to 2 super Yang-Mills theory. So that was one. So generically not true, Montan-Olive duality generically not true, but in supersymmetric theories it may be true. But there is a second problem. That was once one problem was the BPS limit. Second problem is that this duality relates, the way we see it, objects W plus minus, masses of W plus minus and monopoles. But these are spin 1 and these are spin 0. So, but spin does not change under duality. I mean, so this is, I mean, you may arrange this to be true, but it still is not enough. The second problem is W plus minus are spin 1 and M plus minus are spin 0. So even if you have arranged that mass spectrum is same, couplings are same, but this property is not there. So therefore duality symmetry cannot be true.
So how do we show that the spin of the monopole is 0?
Is spherically symmetric. Didn't we construct it? So even supersymmetry may not help us generically, but is there is a particular supersymmetric theory where this can change? There is one. N equal to 4 SUSY symmetry, supersymmetric Yang-Mills solves this problem also. The one you did in the exam was n equal to 2. We'll perhaps understand why it's n equal to 2. There you don't have this property. But n equal to 4, if you do it, you have this property. Then 3. When we studied duality for electromagnetic theory Maxwell's theory, a theory with one coupling with another theory with another coupling which is inverse of the coupling of the first theory. Right? The couplings were each other, for Sine-Gordon theory and massive theory model, the couplings were inverse of each other. So it's possible to imagine that a theory may not have a spectrum which is self-dual, but it may this duality transformation may give you another theory which is dual to the first theory. So the Montan-Olive duality may give this duality, Montan-Olive duality may relate one theory, one theory with another with inverse coupling, like the Sine-Gordon and massive 3-model duality. While n equal to 4 supersymmetric Yang-Mills theory is self-dual, which means within the same theory you have particles which are related in their masses and electric and magnetic fields by duality, like the Maxwell's theory, modified Maxwell's theory that we studied. N equal to 2 supersymmetric Yang-Mills theory is of this kind, is that under duality transformation it maps one theory to another theory. Small coupling SU2 n equal to 2 SUSY theory is dual to large coupling U1 n equal to 2 SUSY theory. And vice versa, which means that large coupling SU2 n equal to 2 SUSY theory is dual to small coupling U1 n equal to 2. Once you realize this property, then you also immediately realize that if this is true, then in order to understand the large coupling behavior of SU2 n equal to 2 Yang-Mills theory, I can study it in this picture where it's a small coupling theory. So which means I can study it perturbatively here. I can extract out non-perturbative large coupling answers of this theory by studying small coupling perturbative properties of this theory. So this gives you a very powerful tool of understanding large coupling behavior of quantum field theories, because you are able to map it to a weak coupling theory. The couplings of these two theories are related inversely. And this property has been used to work out exact quantum mass spectrum of the theory. Not only perturbative corrections to the masses, which is what normally we know how to do it, but you can solve this theory for masses exactly. And these are, I don't know if we'll get to discuss these things or not. This is what is called, these are papers by Witten and Zyberg in early 90s? I don't, 94. Okay. Now to understand this picture a little better, let me do some little bit of algebra. Start again with Georgi-Glasser model. So anyway, bottom line here is that Montaigne-Olive conjecture is not true, generically true, but it's true for n equal to 4 Yang-Mills. Let me do some little bit of rewriting. So go back to Glasser-Georgi model, and to start with, let me put theta equal to 0. What did I have? I had S to be d4x minus 1 by 4 f mu nu b f mu nu p, or maybe no, let me put theta non-zero, I'll put a theta term also, plus half d mu phi b d mu phi b minus v phi, and then let me add the theta term, theta e square by 32 pi square f mu nu b f dual mu nu. This is what this was. Let me do a rescaling. See, this rescaling, we replace a mu by new a mu prime, which is a mu by e. Or just simply let me write, replace everywhere a mu by. This we have done several times, right? We did this rescaling. And in the exercise that you had in your exam also, your Lagrangian was given with this scaling. What does this do? This changes the action. This term has two A's, and then it has also three A's and four A's, but F written here, the interaction term is also has an E in it, right? F here and covariant derivative there is an E here. So if I scale, replace a by a mu by E, there will be a mu by E square, one E will cancel here, so I will have a 1 by E outside. So I have a 1 by E square for two such terms. I will also do the scaling, replace phi by E. I had not done that in the exercise I gave you. Now when I do that, this becomes 1 by E, has a 1 by E, that cancels this, but there is an extra 1 by E from this and extra 1 by E there. So even this term has 1 by E square. Now remember, V phi in this theory was lambda by 4 phi square minus a square. Whole square. Now if I replace phi by E divided by E, I can take that E out, I will get E to the e to the power, what do I get? 4 here, right? But then a square will also have an E. So let me replace also a by a times E, or replace a times E by a. But then I have here 1 by e to the 4. The e square I take out. I also redefine lambda by e square to be new lambda. So V phi now is new lambda phi square minus a square square. And let me also write f mu nu b is d mu a nu b minus d nu a mu b minus epsilon b c d a mu b a nu d, and covariant derivative of phi b now is d mu phi b minus epsilon b c d a mu c phi d. So no e's anywhere. Now that leaves this term. Now we argued that f picks up an extra factor of 1 by e. So here also f picks up 1 by extra factor of 1 by e, and this one, another one that I have taken out. So I write that term as it is. If I do this, I can rewrite this whole action in a particular way. Say it again.
Last term will not have an e square.
Yes, but I have taken 1 by e square completely out. 1 by e square. So that will cancel this.
And so there will be an overall 1 by e square.
This will give me 1 by e. This will give me 1 by e. So this will cancel this a square. So theta term is without e. But since I have taken 1 by e outside, I have kept e square inside. Now this whole action I can rewrite in a particular way. 1 by 32, let me write it first, times imaginary part of the integral d4x times tau minus fb mu nu minus I f dual b mu nu square plus 4 d mu phi b square minus 8 v phi, where tau is theta by 2 pi plus 4 pi I by E square. Now let me check whether this is exactly that. Let me expand this out. This is f square and square of this term. I square is minus 1. But then I have f dual mu nu, f dual b mu nu. There is one term like that. You should be able to convince yourself that this is same as yes, Minkowski. We are doing all Minkowski. Is it clear? Just check that, that's what it is. So what it means is that f square term and this square term is the same, because this is a minus that object, so this is plus. So I have twice f square term multiplied by this object, multiplied by 1 by 32 pi. And if I take imaginary part, which means I take this part only, 4 pi by E square times twice is that exactly that the first term? Eight, 4. Then there is a cross term here, twice f dual f. That has an I in it. And since I have to pick up the imaginary part from here, that will come from tau equal to this term. So theta times f dual with the numbers twice this, if you add it up, this must be the answer. Have we done it right? And similarly, I think this coefficient will also work out, because this is again for imaginary part, which means it must come from here. 4, 16 pi divided by 32 pi is 1/2. So this is only a rewriting of this action. Now this action has some interesting property. Recall theta going to theta plus 2 pi is a symmetry of the theory. We had argued it last time. Why is the symmetry of the theory? Is because what is relevant is I times s theta term, which is this. And s theta term is I times theta times that s instanton density integrated. And we had argued that this object is an 2 pi times an integer, when we normalize it like this, right, and then this is an integer. So if I shift theta by 2 pi, this object doesn't change. So theta shifting by 2 pi is a symmetry of my theory. That's how we also argue that theta is an angle, right, with period 2 pi. So which means if I write theory with functional integrals with this action, or I write functional integral with theta replaced by theta plus 2 pi, the theory should be same. The answers from such functional integrals should be same. That means theory should be invariant under tau going to tau plus 1, because theta shifting by 2 pi means tau shifting by 1. So this theory written in this particular way, we discover is that you have this complex parameter here, but if you shift this complex parameter by 1 unit, the theory has to be invariant. So physics has to be unchanged. Because action will shift only by 2 pi times an integer. Because under this object, action will shift from action plus 2 pi times an integer. Now let me look at for theta equal to 0. Let me take theta to be 0. At the tree level in this theory, we have seen that there is a duality, and the duality was E going to G, and G is 4 pi by E. Now what does this imply? This implies that if I look at 4 pi times I divided by E square, which is this combination, how does this change? This changes as 4 pi I divided by 4 pi E square. Let me simplify this. 1 4 pi and 1 4 pi goes away. So this is I E divided by 4 pi E square. Is it clear? Simplify this. E square goes away. E going to G, which is E going to 4 pi by E, right? Because G is 4 pi by E, right? So E going to 4 pi by E square. So simplify this, this is what it is. Now I can also rewrite now this as minus 1 by 4 pi I by E square. Rewrite this way. I down gives me an additional sign. So this duality for this combination means that it is it shifts to minus times inverse this combination. So for theta equal to 0, what it means is that tau goes to minus 1 by tau. So what does it mean? Is that electric and magnetic duality, E going to G duality, in this language is tau going to minus 1 by tau for theta equal to 0. So I'll take 5 more minutes and then close this. Let me require that this duality holds even when theta is non-zero. Then transformations, tau going to tau plus 1 and tau going to minus 1. These transformations are generators of a group. It's a generator of a group that we already talked about earlier. These transformations generate transformations, arbitrary transformations of tau going to tau prime by, let me use the same notation, m tau plus n divided by L tau by k, where m, n, L, k are all integers and m, k, n, L is 1. And these transformations form a group SL to Z. These M, N, L, K. The set of 2 cross 2 matrices with unit determinant and entries integers. 2 cross 2 matrices, determinant 1 with all the entries integers, that form a group, and these are the generators of this group. What does it mean by generators of the group? Is that by successive such transformations I can generate an arbitrary transformation of this kind. A sequence of such elementary transformations in some order, whatever arbitrary order, will generate these transformations. And what sequence and what order I have used will give me different values for these m and n and k, which will be satisfying these properties. This is what we had already seen, right? We had talked about that the lattice, charge lattice lives, the charges live on a lattice which have the symmetry under SL2Z transformations. So we have seen this. An important property of these transformations is that these transformations leave imaginary tau, the imaginary part of the tau, imaginary part of tau, this condition unchanged. So if you have imaginary part of tau which is positive, under these transformations always stay positive. This is an exercise, do it. And for our case, notice imaginary tau is 4 pi e square. It's always positive. Is that clear? The imaginary part of tau is always positive for our case, and this property always stays true under these transformations, which means these transformations live on the upper half complex plane. They move values of tau from different points in the lattice in the upper half. In some places there are names given to these objects. This is called T duality. This is called S duality. So if we want now this to be a property of a full quantum theory, which we are restating these statements we made here, generically it's not true. But for n equal to 4 Yang-Mills theory, this would be true. So what does that mean? Is that if I write the corresponding action for n equal to 4 Yang-Mills theory, this was Georges Glashow wrote it. Then that action, whatever calculation I do, function, quantum calculations I do with that action, which means write down partition function and do functional averages of interesting operators, all that objects, they will have the property that the answers will be unchanged under changing tau by tau plus 1 or tau to minus 1 by tau. Not in this theory. In this theory I only traced it out what is the symmetry I want. Because we know on this theory we argued that the BPS limit is not respected. But in that theory, BPS limit is a quantum theory limit. Is that clear? Okay, I think.
All of this is true only
Classically. I think we'll stop there. And I don't know, the people who proved that this is the case for n equal to 4 Yang-Mills theory, let me list them. N equal to 4 Yang-Mills. Font, Ibanez, Lust, and Quevedo is a physics letter paper, B249, 1990, 35. And another guy who did it was Ray, PRD 43, 1991, 526. But they used complicated string theory to prove this. But we may see it even doing without that. at least some properties of it. So maybe next time I'll start on discussion on supersymmetry. Is that all right? And we'll try learn how to build supersymmetric theories.